So, Ms. Navickas, I see that you poured equal amounts of 3 different types of water into 3 of the same size cups, and that now then you're going to taste each water separately to determine if they have different qualities of taste.
Right.
I guess by tasting it, you have the ability, we have the ability to have different chemicals, could be on our tongue, if there's different chemicals in there, you'll be able to sense that taste. So what is it that you're changing again in this experiment?
Our independent variable is that we have different types of water that we will be trying.
So the independent variable is the first thing that you did when you poured the 3 different types of water, is
Right.
the independent variable.
Right.
So in the end, you're going to figure out the different tastes. Now, taste isn't like it doesn't seem scientific.
Right, it's not a number.
It's not a number, so it's more of a quality. I guess you'd call that that's called qualitative data.
Right.
And sometimes we use that qualitative data, like, for example, this could be a red pen, but we have different shades of red, so we can only describe this not very scientifically by saying red. So why don't you, so the dependent variable will be how you perceive taste, and you may have, I'll have to see how that is. So why don't we test and get some data on your water? So you're drinking a drink.
Alright, so I'm going to start with cup number 1, just to go in order.
And I will write down the results, which is the dependent variable, the data. What do you think about that?
Okay. Cup number 1 just tastes like basic water, no real flavor to it.
No flavor?
No real flavor.
Just basic water, whatever that means.
Whatever
We'll
that
see.
means.
Try the second one. So that's cup
Okay,
number
so
1.
trying number 2. This one tastes a little bit better. It tastes like it has more of a watery flavor.
Watery flavor?
We'll see what that means.
Well, yeah, we don't really know because this is a whole new experience for you.
Right.
Okay.
Okay, so now I'll try cup number 3. This water tastes like it has more in it than just water. It has more flavor to it.
More flavor.
Yeah.
So you would say cup number 1 has no flavor?
No flavor. There's
Cup
no...
number 2 tasted better?
Yeah.
And cup number 3 has more flavor?
More flavors in it.
Has
You
more...
taste like it's not just water, like there's something more in it.
Something more in it?
Yeah.
If you want to try it one more time?
Yeah.
And then go backwards, and that will give you a better sense. So you're taking...
Yep.
And the second one?
Mm-hmm.
Okay.
Yep.
Still have that?
Yeah.
Okay. All right. So the question is, so you're saying not all water is the same.
Right.
So there's something different about these 3 waters. Let's do some more tests on it.
Sure.
Okay. So one of the things that we have that we can do is we can test to see if there are different kinds of minerals in there, like or things that are in there like minerals, because when we drink water from the faucet, right, we get water from our faucet, where does that water come from? You know, that water can come from either where?
Can come from a well.
A well,
Right.
or a reservoir.
Right.
And what's usually a well is under the ground, and a reservoir is in a lake or a pond, and
Right.
there's all rocks around it, and there's stones and soil, so that could affect the kind of water we drink.
Definitely.
Yeah. And then it has to go all the way from the reservoir to where we live, and there's pipes
Right.
and things are going through. So that could change what's in the water too.
Definitely.
And if you have well water, it doesn't go to a water treatment plant.
Right.
But faucet water, I think here, goes through a water treatment plant.
Mm-hmm.
So there they may add chemicals like chlorine to
Yeah.
it, and that could change the quality of the water. So it seems that by tasting this, not all the water is the same.
Right. That's the most important part, is that these waters didn't taste the same.
So even though we teach that water is H2O,
Mm-hmm.
So pure water, I wonder if how it could ever exist. But the molecule of water may be different than the solutions of water, which are really not, quote, pure 100% water.
Right.
There may be things in it.
Mm-hmm.
Okay, so let's do some tests to see what else could be in it. One of the things we could test for is if there is minerals in there or rocks or metals in there. Metals
Yep.
would be a good thing to check for. And I have something that we can do to check for metals.
Awesome. What would you use?
I have what's called a conductivity probe, and I'll show you what that's like, and I can even show you how it works.
Awesome.
And if you had a physical science course last year, you probably learned that, and I'll show you with the battery how it works. We have 3 different kinds. Two of these two kinds give you what's called qualitative data. So for example, when I turn this on and I touch a metal object, which I can find if I, oh, right, we have a metal object nearby. If I can touch this particular area right here, on here, and if the battery is going to send electrons down this wire, and when it touches the metal, it should either beep, because now the electrons can flow through the metal, because metal is a good conductor. Why aren't you beeping? There we go. I hear you wanting to beep, but what's going on here? Let's fix this here. Maybe it's a loose cord. There we go.
There it goes.
So what's happening is the electrons are going down the wire, across the metal, and creating a complete circuit. When it's open like this, there is, let's see, when I touch, I'm creating a complete circuit here, so the electrons can move. But when it's open, it's a closed circuit. Open circuit. Open circuit means there's a gap. So what if I put this into a solution? If there's metals in it, like the cups, could I show that it'll help conduct electricity?
So you mean that when this goes in the water, it'll start beeping if there's metals in it?
That's what I mean. Good. And I also have another one here that will light up, but not, let's see if we could test that one here. I'll put it on this metal here, and if it lights up, if my battery is working well and everything's just right, it should light up. And we'll try that one. How come you're not lighting up? Here we go. Just had to make sure that it's touching it well. I had to push it on there. Okay. So it's lighting up, and that means that. The other device I have is actually, it's a digital multimeter, and it actually, if I turn it on, there are numbers on here. So this is actually a more quantitative data, and numbers are what scientists always want to strive to get numbers, because numbers can really show us change much more than a beep or not beep. It can show us increments of change and measurements that, and we want to always strive to create experiments that have numbers. But for now, we're just going to use what we have, and I'm going to show you that I'm going to be measuring resistance. If you can remember from last year's course, that resistance, if there is a high resistance, that means electricity can't flow through it. There's no metal. If there's a high resistance, that means there's no metal to help the electrons to flow through the metal and create a closed circuit. So for example, if I touch this surface of the desk, which I'm doing right now, or this pen, let's say, I know this pen is covered with plastic like that. And if I do that, I will not get any, I have what's called 1, and the 1 is like considered a very high resistance. But if I take it and touch it to the metal, like I did before, you look over here at this metal device and try to see the number that's on the screen here, and I hopefully will get some kind of conductivity number. See how it's going down? I'm down to 0.000301. This is conducting electricity, and because metals have a lot of electrons in their outer valence. We'll go over that later on, and conductivity is happening. I am closing the circuit. There's a battery in here that's providing a source of electrons, and now they have a place to flow. So if I put it on plastic, I have no more flow of electricity. So I could actually use this too to help me determine how many minerals there are in our types of water.
So if we use this conductivity probe and put it in our water, if there's metals in the water, then it'll be a very low number.
That's right.
Okay.
Because it's saying electrons are having no problem flowing through. There's no resistance.
Right.
If it's a high number, it means there's not any metals to help the flow of electrons.
Okay.
Okay, so ideally what we would do is we would start off with the same 3 cups, the same amount, but at this point we're going to save a little bit of time and just put our conductivity probes into each one. Now we do have to be careful with something, because if we put our probe into each cup, what could happen is I might contaminate the tips and I may have to rinse them off, so I'm going to get another cup to rinse things off with, okay? So in the meantime, I have some distilled water over here, Mr. Dickus. See this? And this distilled water, and distilled water is an interesting type of water. You can buy it at the store. See it over here? Distilled water is made by boiling water, and when it becomes a gas, like steam, water vapor, or steam, you can cool it down on a cold surface, and when it condenses into another liquid, it leaves behind a lot of the minerals. It's not 100% free of minerals and metals. When I say minerals, I often imply metals are in there too. So let's test our water. Let's test. We'll have our rinse cup here. Yes, because that's.
And I labeled it rinse cup so that you don't get it confused with any of the other cups.
Awesome. So smart to label everything, because it's so easy to get confused. Okay, so we have our rinse cup. So we're going to look at cup number 1, conductivity. So what are we doing now? We're starting a whole new experiment.
Right.
And in experiment number 2, what are we changing?
The different types of water.
Oh, so it's like the first one. We're still working with the different types of water.
Right.
But what are we measuring now? What's our new dependent variable?
Our dependent variable will be the number that we get from our conductivity probe.
Okay, so let's see how that works. All right, so here we go. So we're going to measure our results, cup number 1, and I'm going to make sure things are written down, because that's how I keep my data very careful, and I'm going to label it carefully on my paper. And I'm going to put the conductivity probe in here, and I noticed that my number's changing. It went down from 1, now it's going to, wait, just happened here. Now it's at 1. Does that make sense? Yeah, oh wait, it's actually, no it's not. It's at 1, which means a very high resistance. Remember from before? I don't know, there must have been some chemicals on here getting diluted, but it's a 1. So I'm going to put down 1 for cup number 1. So it is not helping electricity flow. I'm going to stick it in my rinse cup. So it's got a very high resistance. There's not any metals in there. That's interesting. Let's try. I just rinsed my tips of my probes out, and I'm going to put it in cup number 2. So cup number 2. Oh, cup number 2, the numbers are changing. And they're not at 1 anymore. There's definitely a number there.
Mm-hmm.
And so that particular value I'm going to write down is definitely not like the one that we decided was the one that doesn't conduct electricity before. For remember the pen was made of plastic, it had a 1.
Right.
And that meant that it didn't conduct electricity. It's it's insulator. Let's try cup number 3. Number 3 also has metals in it. I see a number here. It's not 1. There's conductivity going on. So that number was very close to the other number almost. Okay. All right. So there we go. So now we know that testing, I could read, and I'm rinsing again. If I want to go back and check it again, I can always check for this one here. Again, it's at 1. This one here really quickly. It's definitely not 1. I'm sorry, it's changing here now. And then this one here is changing. Okay, thank you. That's good. All right.
It's always good to double check just to make sure that your results are accurate.
Yes. Okay, so now that's our second experiment. So now we know that cup number 1 doesn't have any minerals. Cup number 2 and 3 do. That's interesting. All right. Now, what I did, and you may not realize this, but what I did is I know what I put into those cups ahead of time. And I didn't want Ms. Navickas to know, because if she knew, she may have thought about the taste part as being, oh, I'm going to remember that I really like that kind of water better.
Right.
and you're going to be biased in your decisions.
Exactly.
So what we did was called a blind study, where I knew, and ideally I would put the numbers down and have someone else test her.
Right.
So that was called a double blind study. But she didn't know. I know what's in cup number 1, cup number 2, and cup number 3. And I'll tell you.
Okay.
Okay.
Yeah.
So cup number 1 was distilled water,
Okay.
which is the stuff that we're rinsing it with. And I
Right.
chose that as a good rinse because I know it was boiled and condensed, and it shouldn't have a lot of metals in it. And
Okay.
you said it had no flavor.
So that's interesting.
Yeah, and you didn't know it was that.
No.
And then the cup number 2, you said tasted better.
Right.
And that was Poland Spring,
Okay.
which a lot of people like to buy and drink.
Right. That's
And
what I drink.
supposedly it comes from natural spring water, so it has touched the earth and has minerals in it and metals
Okay.
in it. And cup number 3, you said had more flavor,
Mhm.
and that was tap water.
Okay.
And maybe that when I drink the tap water here, I can taste some chlorine in it too.
Definitely. There was definitely some flavor of chemicals in there.
So unless you know what chlorine tastes like,
Right.
you wouldn't know. But I know we put a lot of chlorine in our water in the summertime because we want to kill the bacteria. Levels are higher, especially more so. I find out that they put more chlorine in the water in the summertime than the wintertime because it's hotter water will have more bacteria grow. It's interesting to think about
So
too.
then that makes sense that our conductivity numbers were 1 for the distilled water, and then they increased for the Poland Springs and the tap water because they had metals in them.
Yeah, it
Okay.
does. So
Interesting.
there's an interesting experiment that we can try just to see how this conductivity really works. And when you're in a biology class or any class that you're working with, chemistry even, you're going to be making solutions.
Okay.
So what is a solution? So a solution is something mixed with water.
Right.
We'll be making solutions. And in this course, when we're doing osmosis and things of that sort. So why don't we try another experiment? Let's see what happens if we take distilled water and we add a metal to it. Would it change the conductivity?
Okay.
And maybe what we can do is also use the beeper. This way you could hear it.
Right.
We could try that instead. As a matter of fact, I wonder what would happen if we can get this. I'm not sure if this is going to work right now, but we could try it really quickly. Oh,
Wow.
cool.
Awesome.
So what I just did, and you didn't see that, but I'll hold this up. This is cup number 1, which is the distilled water, and I'm going to use the conductivity probe that doesn't have numbers on it, that just makes the beep, and I'm going to put it in cup number 1. I don't hear any noise. I'm going to rinse it, shake it off, cup number 2. I hear a beep. I don't know if you do, but it's
Yeah.
definitely a beep. Rinse it off, go to cup number 3. That was louder.
Yeah.
So you were right in the way that you said you'd sense these chemicals. Your tongue has amazing receptors on it. All right, so that's great. So let's try another experiment. This time, we know that these 2 have metals in it. Let's take the distilled water here, which was cup number 1. And I happen to have distilled water, and it's going to be in all the cup number 1s. And now that you know it, this is all distilled water here. You didn't know that beginning, but we're going to do a new experiment. And let's create a situation where we add metal to 1 and see what happens. Oh, well, wait a minute. No, let's try something before we do that.
Okay.
Let's try to measure another chemical that we can't see.
Okay.
And
What
that's the
chemical?
hydrogen ion.
Okay.
We can't see hydrogen ions. And do you know why hydrogen ions are important?
No, how come?
Because they're involved in the pH scale.
Okay.
And pH has to do with acids and bases. So I'm curious, do these waters have the same pH?
Well, how can we find that out?
We can find that out easily. I have some pH paper. And hydrogen ions are hydrogen atoms that lost an electron. They float around in water solutions. It's always a water solution that they're in. And different water solutions could have different amounts of those hydrogen ions. If there's a lot of hydrogen ions, then it's more acidic.
Okay.
And if there's a lower amount of hydrogen ions, then it's basic. And you may wonder why we need to know that, but the human body and cells have to have a special balance of hydrogen ions in order to keep their proteins safe and everything working properly. So I have something called pH paper,
All right.
and
let's try
that
it.
is a way to measure it. So here we go. this pH paper here is on a scale of 1 through 12. So I'm going to give you a piece of same pH paper, so we're going to keep things constant.
Right.
There may be different kinds. It's the same brand. There you go.
Okay.
And I have a piece here too. And if we want to do it all at the same time, we could. That would keep things constant. So why don't we dip these into the water, line them up carefully with the cup so we don't confuse which one, and see what happens. That might take a little while for it to change. I'm not sure. Is this one different?
Oops.
Look, they're all around pH 7.
Yeah. So what does pH 7 mean?
pH 7 means that, well, technically it's a certain concentration of hydrogen ions, and it's kind of confusing to understand that it means that there's 10 to the minus 7 molar hydrogen ions in there. It's kind of like a percent in the sense of how much hydrogen ions are floating around. The middle one here looks a little greenish.
It does.
It does. It looks like it's almost, but we have a more sensitive one. I actually have one I could tell even more sensitive.
Okay.
Try this paper, and I'm not sure. Do you want to open that up and try that?
Okay.
Here we go. Here it is. I found a sensitive one. Yes, this is another type of sensitive paper, and it goes into the range of 5 to 8.5 instead of 1 to 14. So we're going to try that one. I'm just curious because that was surprising that they're all pH 7, but not too surprising. You would use what's called a pH meter, and you would get quantitative numbers, and you would see much more detail, be more precise. So there's your piece there, and we're going to try this one. We have another color scale to match with. Ready?
Okay, go.
We're dipping it in here now, and we're going to hold them up and see if they're the same color, and it looks like, yeah, the pH is the same. Okay, but at least we were able to tell that.
Yeah.
Maybe it'd be nice to compare something that doesn't have the same pH, and I can do that really easily for you. What I could do is put a drop of acid in one of these.
Okay.
Let me show you. I have that right here. This is a solution in here of water that has acid in it, and I'll get a little cup, and I'll show you that when I squeeze a little of that in there, you could take you can use the other pH paper too. And what we'll do is we'll see, what does it look like when there's a lot of hydrogen ions? I mean, if you look at what I squeezed in there, it looks just like water, doesn't it? Is that the one that's changing? Not that acidic, is it?
Oh, it's turning green on the side.
It's turning green. Which one was that, the yellow paper?
Yes.
Green, so it's around pH 5, but that's really not very strong acid, is it? Oh well. If it was,
you can see just a little bit on the side of this is turning green. I don't know if you can see it in the video. Kind of hard to see.